Good morning and welcome to topology classes. Today we will discuss about some examples of topological spaces. Last class we have seen the definition of topological space. So last class we have seen topological space. What was topological space? It is of X script T type where X is a set and tau is a family of subsets of X, and which should satisfy three conditions, which will satisfy three conditions. What was the first condition? Was script T contains, or we can say that your entire set and empty set, right? That is, empty set belongs to script T and X belongs to script T. And second was script T is closed under arbitrary union, and third condition was script T is closed under finite intersection. Finite intersection. These the two things we want to mention here. And last class we have stopped with cofinite topology. Cofinite topology. What was cofinite topology? Cofinite topology means a set X with a topology tau, such that what is the specialty of this? If some B subset of X, then B belongs to tau implies X minus B is finite. This is the idea. Okay, that means we will say that complement is finite. And we have seen that if X is finite, this topology coincides with the discrete topology. I repeat, if X is finite, it coincides with the discrete topology. Now we will examine what type of sequences may converge in this topology. So, as a theorem, let X tau be a topological space with cofinite topology script T, let a sequence we are considering, let Xn be a sequence in X, then the sequence is convergent if and only if there is at most one term of it, one term of it, which repeats, which repeats infinitely often, infinitely often. So let X be a topological space with cofinite topology, strip T, then a sequence in X is a convergent if and only if there is at most one term of it which repeats infinitely often. That means in cofinite topology, a sequence converging means the sequence should have terms which is repeating, and the number of terms which will repeat infinite times should be at most one. So how we can prove this? Proof. Suppose first that, suppose sequence xn is convergent. Sequence xn is convergent. Let if possible, a comma b, a and b are two elements or two distinct values assumed infinitely often by the sequence, that means you got a sequence xn as a b b b, then a b b b, like that. Okay, infinite number of times a and b are occurring by the sequence. Then there are infinitely many values for n. Then there are infinitely many values for n for which the sequence term xn is outside x minus singleton b. Okay, x minus singleton b. But mainly the term should be a, because a is infinite time occurring. So x minus, sorry, the term is b. B is occurring infinitely many times. So x minus b does not contains any of these b's. But x minus singleton b is an open set, containing a, containing a. Because x minus b means definitely a belongs to x minus b. Am I true? Sorry, x minus b. Then you consider x minus of x minus b. So x minus of x minus b you will reset as singleton b, right? So what this follows is, which implies this is finite. So complement is finite means evidently your x minus b belongs to the topology. belongs to topology. Now any element belongs to the topology means we will say that it is open. So x minus b is an open set containing A. And if x and y converges to A, it's an open set containing A. And if your sequence xn where converges to A, then x minus b will contain xn for for all except finitely finitely many values of n. Thus we see, which implies your xn cannot converge to A. Similarly, we can see that it cannot converge to B also. Similarly, it cannot converge to B also. What's the reason? If we are taking B, you can take x minus A and proceed similarly. But we have assumed that xn is converges, so xn should converges to some another point. But we assumed our sequence xn is convergent. So there exists some c belongs to x different from a and b, different from a and b, such that the sequence xn should converges to c. But then consider the set x minus ab is an open set, again its complement. You take the complement, you will get the set a comma b, which is finite. So this is an open set containing c, but it does not contain the elements a and b. Now what is the specialty of a and b? A and b are those elements which repeats infinitely often. That means this open set contains lots of terms which are missing from your sequence, which fails to contain xn for infinitely many values of n. Thus we get a contradiction. This shows that a convergent sequence a convergent sequence can assume can assume at most one value one value infinitely often. Now conversely suppose xn assumes at most one value infinitely often. Then then we have to show that the sequence xn is convergent. It's convergent. If there is no such value, because at most we have set no such value, then it converges to every point of x. Since since in such a case in such a case such a case every non-empty open set every non-empty open sets contain all all except finitely many terms of the sequence. If there exists no such value, then the sequence converges to every point in X. The reason is you take every non-empty open sets contain uh, all elements except finitely many terms of the sequence. Okay, then if there exists no such a repeating term means we can take any non-empty open set, then that will contain uh, all except finitely many terms of the sequence. That means the sequence may converge to any point. Now assume there is only one term assumed infinitely often. Now assume there is only one term b assumed infinitely often in the sequence x. Then we prove that then we prove that the sequence converges to B. The sequence converges to B. Let V be an open set, be an open set containing B. Open set containing B. Then x minus V. So x minus V, it is x minus V is a finite set because V containing open set B. This is B, this is V, and you're having set this to be as your x. So x minus V means it should be finite because this is an infinite set. X minus V is a finite set. It's a finite set, and every element in it is assumed. In it is assumed. How many times? At most one, because we have seen that uh, only B is occurring infinitely many times. It assumed at most, not one time, finite number of times. At most, a finite number of, times. By the sequence x. Hence, x minus v contain how many times? At most finitely many terms of x. At most finitely many terms of x. Consequently, xn converges to the repeating element b. Moreover, in this case, see, you are seeing that or we have just proved if B is an infinitely occurring term in an co-countable topology, cofinite topology, then this sequence converges to B itself. Now, is there any possibility that this sequence may converges to some other point? That's the thing we are discussing here. There is no such possibility because when you're having, suppose your sequence xn is converges to some other point C, then definitely you can take an open set which containing B. Then if you are removing that B from this set, infinitely many terms of the sequence may lie outside the open set containing C. So moreover, in this case, Xn cannot converge to anything else. To anything else. since since x minus b is an open set which misses infinitely many terms of it. Thus, we can say that in a cofinite topology, uh, if a sequence converges, hence the theorem. If a sequence converges, then it should have at most one element which is repeated infinitely many times. So, third example is our cofinite topology. Example 4, we are having co-countable topology. Once you studied co-finite topology, you can easily guess what is the definition for co-countable topology. A belongs to this collection of topology T means if our condition should be x to x script T, x minus A should be countable. X minus A should be countable means either x minus, that is either x minus A is finite or denumerable. Okay. Now I'm leaving for you to work. One question for you. What type of sequences will converge in co-countable topology? Co-countable topology. What type of sequences will converge in co-countable topology? Just you work it out, those co-countable topology by yourself, and submit whenever I am asking for it. Okay. So with this, I am winding up today's session here. Thank you for your patient listening. Thank you.